Today we're going to look at 3 different ways that atoms can be joined together. We're going to look at metallic, ionic, and covalent bonding. And keep in mind what we saw in the lab that we conducted the other day. The first type of bonding we're going to look at is metallic bonding. And we can guess by the name that it's going to be occurring in metals. It consists of closely packed cations, those are our positive ions, surrounded by free-floating valence electrons. Remember, electrons have a negative charge. So the electrons that are in that outermost level, that are not part of a full ring or a full shell of electrons, are going to be available to move around throughout the entire metal. And our substance would look kind of like this if we zoomed in really close. It could be either a pure metal, one of the metals that's on the periodic table, or it could be an alloy, which is a mixture of different metals. Things like brass and pewter and bronze and things like that. So in our diagram, we see that we have these positively charged cations dispersed, and between them we have these negatively charged electrons. And these things are free to move around. They can move in there, can move over there, can move over here, it could move over there. These are just moving around all throughout, which are going to give metals some of the unique properties that we know that they have. One of the things we know about metals is that they're good conductors of electricity. And if we think about what electricity is, it's just the movement of electrons, of charged particles through a substance. So as long as we have those free-floating valence electrons, they're free to move about. We refer to those electrons as the sea of electrons. All of these moving around in there. So that sea of electrons is free to move around, which means that electricity can flow. Metals are also capable of being drawn into a thin wire. They can be stretched out. We say that metals then are ductile. And metals are also capable of being hammered into thin sheets, and that property is referred to as malleable. And the reason why they have that property is that that sea of electrons, again, is free to move around. And so whenever you start to move that material and the positive ions are getting closer together, instead of getting too close and repelling and breaking apart at that location, those electrons, if they have enough time, will move into position between those positives and kind of keep them from coming into contact and repelling. So it cushions the positive ions from coming in direct contact, which would cause the metal to snap or break whenever they would start to repel. It's all about opposite charges. We want the opposite charges to be attracting. If like charges come to contact, they're going to repel and it will break. Okay. That is metallic bonding. It only occurs with metals, those elements that we find to the left of our staircase on the periodic table. Our next type of bonding is ionic bonding. And again, we can look at the name and figure out what it's talking about. It's talking about ions, those things that are charged. It can either be positive or negatively charged. And for an ionic bond, we're going to have one of each. It's a bond formed when electrons are transferred between atoms with largely different electronegativity values. What that means is that you have something that's on the right-hand side of the table that really wants to hold on to the electrons that it has, and it really wants to take some more from some other elements. And it's going to bond with an element that's on the left side of the table. Those that have fewer valence electrons, they really want to get rid of them. They want to give them to others so that they will then have that lower energy level filled with electrons. So let's look at sodium and chlorine. Sodium's in the first column, the first group. Chlorine's in group 17 or 7A. So since sodium's in group 1A, remember that means it has one valence electron. And since chlorine is going to be in group 7A, that means it has 7 valence electrons. So this one valence electron out here on sodium, sodium wants to get rid of it. Chlorine has 7. It has a location here where it wants to have one more. So sodium will donate that electron. Sodium then will take on a positive charge because it lost a negative electron. Chlorine will take on a negative charge because it took in that electron. And then we have an attractive force between them. An electrostatic force is what a bond actually is in an ionic compound. It's just an attraction between the positive ion and the negative ion. And whenever they're all held together, they're going to have a lattice structure. Sometimes it's called a crystal lattice structure. And those electromagnetic attractive forces hold it all together. It'll look like this. And we do not have molecules. This is representative of NaCl. So this would be like a Na, and this would be a Cl. This would be an Na, and they just kind of alternate as we go around. So when we look at just the smallest ratio of the elements in that compound, remember it's going to be called a formula unit. So ionic compounds do not have discrete molecules that are separated from one another. Instead, they have formula units. Some properties of ionic compounds that we saw in the lab as well. Most are going to be crystalline solids. We know that salt is an ionic compound, and if we just kind of think about what properties salt has in NaCl, then we'll kind of be able to remember the properties of ionic compounds. They're crystalline solids, and they have very high melting points. That electrostatic force that's holding them together takes a lot to overcome. Many of them are going to be soluble, which means they will dissolve in polar solvents. Polar things are those substances that have a positive and a negative side to them. So it would make sense that the positive and negative could help pull apart the other positives and negatives. Water is a polar solvent. But if you have a non-polar solvent, something with no charges, it's not going to be able to pull it apart. It will be insoluble. If we melt an ionic compound, if we do get it hot enough to melt, then that will allow it to conduct electricity because we're separating the positive and negative ions from one another, and those charged particles are free to move. Mobile means they can move. But if it's still in the solid form, solids cannot conduct electricity. The positives and negatives are locked into place. They're not going to be free to move about. If we have an aqueous solution, that's whenever you dissolve the ionic compound in water, then that will also conduct electricity. When you dissolve it, you're getting the positives and negatives loose, free to move around. And ionic compounds tend to be brittle, and if you take a hammer to it, it will shatter. Because whenever you hit that ionic compound, you're causing the layers to shift around a little bit, and instead of being positive, negative, all the alternating charges attracting and holding in place, if you shift it a little bit, then all of a sudden you have positive, positive, negative, negative. You have like charges lining up, and they're going to repel one another, and that's the point at which it's going to break. Okay. The next type of bonding we have is covalent bonding. If you look at that beginning part, co means like together or with. So instead of having a transfer of electrons, you're going to have a bond formed when two atoms with similar electronegativity values, they're usually going to be nonmetals, share one or more pairs of electrons. So co, they're sharing it. And they're going to be similar type elements that are able to do this. Neither of them will give up electrons, so that means that neither of them really is taking on a charge. Fluorine is an example of how this bonding can occur. Fluorine has 7 valence electrons. It just needs one more. So if two fluorines buddy up and they each share one that they already have, then we can get that stable noble gas configuration with 8 electrons in that outer shell when we look at it that way. But then whenever we look at this one over here, this one also has 8. So if you take them one at a time, they each will have that stable configuration. Covalent compounds are made up of discrete or individual molecules that are separate from one another. They're free to move around and rotate and just travel around there instead of being stuck in that crystal lattice structure that our ionic compounds were in. Some properties of covalent compounds, they're going to be primarily composed of nonmetals. Ionic was metal and nonmetal. And while ionic compounds tended to mostly be solids at room temperature, molecular covalent compounds can be solid, liquid, or gas. It all depends on their molecular weight. or their atomic mass, however you want to say it. In general, they're going to have low melting points like the stearic acid that we saw in the lab. That's because instead of being locked in that lattice structure with the alternating positives and negatives, the only thing that has to be overcome, you don't have to break that electrostatic charge to have it melt. You only have to break the weak intermolecular forces, the attraction between one molecule and another. And that's a lot weaker. It's a lot easier to overcome that with the heat that's being generated by whatever you have underneath your substance. So it's a lot easier for that to melt than the ionic compounds. Our covalent compounds are poor or non-conductors of electricity because there aren't really any charges to move around. It doesn't matter if they're dissolved or melted or anything like that. Since there's no charged particles, you cannot have electricity flowing through it. And those are the main properties of our different types of bonding. One of the Google forms you'll complete along with this will have some questions about the characteristics of bonding, and one of them will ask you just to identify a substance as either ionic, metal and nonmetal, covalent, both nonmetals, or metallic, just all metals. So both of those will be pretty easy to complete if you just refer back to these notes that we've just covered. The last part that we're going to look at is going to be what you're going to use to complete the back of your formation of ion worksheets, or ions worksheet that you were looking at earlier this week. We're going to draw some Lewis dot structures, and this time instead of just looking at a single element, a single ion, we're going to be looking at how a molecule will be drawn. So we're going to start with diatomic fluorine. Fluorine has 7 valence electrons around it, and if it's going to buddy up, if it wants to share, we're going to put the 7 electrons around it. And it's okay if you're not following the 1, 2, 3, 4 order we talked about before. Let's go with a different color here. So we've got one fluorine and another fluorine. And these 2 electrons here want to be shared. So we could draw it with them just being as a pair in the middle here. And that's how you might see it in some textbooks in the future. Another format, which is the one we're going to use, is that anytime a pair of electrons is shared like that, we're going to put a dash instead. And we still fill in the other lone pairs of electrons. When they're not being shared, we call them lone pairs, L-O-N-E. We'll go ahead and label that one of these things here is a lone pair of electrons. So that dash refers to a shared pair of electrons. That means 2 electrons in that dash. Now that's just what we call a single bond whenever one pair is being shared. There's also something called a double covalent bond, or just a double bond, where it's going to have 2 shared pairs of electrons. Oxygen has 6 valence electrons, so that means that in order for it to be stable, it's going to have to share 2 of them. So we'll draw 2 shared pairs of electrons. That only leaves 4 more that it needs. Because again, if you're looking at just this part, you've got 1, 2, 3, 4 pairs. And then if we look at just this section, we've got 1, 2, 3, 4 pairs again. 4 pairs would be 8 electrons, which is the full octet that we know it wants to have. Okay. If there are 3 pairs of electrons that need to be shared, we would have what's called a triple bond then. Nitrogen has 5 valence electrons, so if it's going to share 3 of them, that only leaves 2 more electrons to fit on the outsides there. And we'll see a little bit more how we come up with those structures on the next page here. There's a whole list of rules here. We're not going to read through all of these. It's just something we can refer back to if we need to, if we get kind of stuck and we're not sure what to do. So the steps you should follow as you're trying to draw these structures, first we need to find out how many electrons we'll need to draw on the page. So we look up carbon. Carbon's in group 4A, so that means it's going to have 4 valence electrons. And then we look up chlorine. Chlorine has 7 valence electrons, and we're going to have 4 of those things. So you can use the calculators if you need to. We have 7 times 4, which is 28, plus the 4 for carbon. So that's going to give us a total of 32 electrons we need to draw on the page. And it's easier to kind of think of them in terms of pairs. So we're going to put that that's the same thing as having 16 pairs. So we just divide 32 by 2 to find out how many pairs. Now, the element that's all by itself here at the beginning is going to be your central atom, the one that you're going to draw in the middle. And then the other things that are attached to it over here are called your peripheral atoms, the ones that go on the outside. And so we're going to draw 4 bonds. It's going to bond to 4 different chlorines, and we just space them out as evenly as we can. And then we need to check those outside elements and see if they need to have a full octet. One of our rules earlier in our notes tells us that if an element's in groups 1A, 2A, or 3A, they don't get a full octet. And we saw that before whenever we drew structures for those elements. Like if we drew the structure for barium, barium would get 2 valence electrons. We'd have 1 there and 1 there. So when I asked you how many things could bond with it, how many single electrons are available for bonding, y'all said 2. Something can bond there and something can bond there. So you're not going to have a full 8 electrons around there. You're only going to have those 4. Remember, each dash represents 2 electrons. So you need to check and see where the element is. Chlorine is beyond groups 1A, 2A, or 3A, so that means it does need a full 8 electrons around it. And if we look here, this dash tells us we already have 2 electrons, and so we need to just add 6 more around the outside edge. And as you go, it's nice to go ahead and count your pairs. We already have 4 pairs, 1, 2, 3, 4, and then I've put 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And once you have those outside ones drawn, then you need to check your central atom and see if it needs any more. It can have a full octet if it's past groups 1A, 2A, or 3A. It has to have a full octet. And if we check carbon, it already has 4 pairs, or 8 electrons from those dashes. So we compare our 16 pairs that we counted as we drew them to this number that's right up here, and it matches. If it doesn't match, then there's something else we need to do. But for that one, it's good. The central atom has a full octet, so do all the peripheral atoms. So let's try this again. We've got phosphorus. When we look it up, it has 5 valence electrons. We have hydrogen. Hydrogen, we have 3 of them, and each hydrogen has 1 valence electron. So we're going to have a total of 8 valence electrons, or 8 electrons. We can just put the E. And if we divide that by 2, that means we're going to have 4 pairs on the page. So our central atom will be the one here by itself, phosphorus. And then we're going to draw 3 hydrogens attached to it. 1, 2, 3. And we'll draw the symbols. And then we check our peripheral atoms, the outside ones, and see if they need a full octet. Remember, if it's in groups 1A, 2A, or 3A, our table keeps going here, but first column, second column, we skip the transition metals, third column. If it's in either of those 3, it does not get a full octet. If we look up hydrogen, it's going to be right here. That means it can only bond to one thing. It can only have 1 pair of electrons on it. It already has 1 pair of electrons right here. You will never see dots around H whenever you're drawing these structures. Hydrogen cannot have any more around it. So the hydrogens are all good. Check the middle atom. Phosphorus is not in these 3 groups. It needs a full octet. It needs 8 electrons around it. Right now we have 2, 4, 6, 8. You draw a lone pair of electrons there. And that should be 4 pairs to match what we came up with up above. For H2O, our central atom is the one that there's only 1 of. So that's going to be the oxygen. And it's connected to 2 hydrogens. We do need to figure out how many valence electrons we will have. Hydrogen, you have 2 of them times the 1 valence electron, plus 6 for oxygen gives us a total of 8 electrons, or 4 pairs. We already have 1, 2 pairs on the page. We check the outside atoms. Hydrogen does not get any lone pairs. Oxygen in the middle, though, needs to have a full octet, so that means we add 2 more pairs. So it has a total of 8 electrons around it. Remember, each dash here is 2 electrons, and it matches. If we have ClO3-, we've got chlorine with 7 valence electrons. We've got 3 oxygens, and each oxygen has 6. And then since we have this negative charge up here, I kind of covered it up, that negative charge means that we're actually going to have an ion that has an extra electron. So if we're adding up electrons here, we've got an extra one, we need to add one there at the end. So that means we're going to have a total of 26 electrons. We divide that by 2 to get 13 pairs. Think about which atom needs to go in the middle. We only have 1 chlorine, so that will be the middle one, the central atom. Then we have our 3 oxygens attached to it, bonded to it. And we check those oxygens to see if they need to have a full octet, and they do. They're beyond that 3A group. So they each already have 1 pair. We already have 1, 2, 3 pairs on the page. So 4, 5, 6, 7, 8, 9, 10, 11, 12. And if we look, 12 is not what we needed. So maybe we forgot to check that central atom to see if it had a full octet. Chlorine right now only has 6 electrons around it, 3 times 2 for the dashes. So that means we need another lone pair there, so it will have a full octet, and then I have my 13 pairs I need. Now there's one extra thing we're going to do with this because it has a charge. Anytime it's an ion, we're going to put the thing in brackets and then put the charge up here top. For the next one, we have NH4+. We have another situation where we have a charge. This time it's a positive charge. So we're going to have 5 electrons for nitrogen. We're going to have 4 times 1 for the hydrogen. And then since it's positive 1, it lost an electron. So we're going to have a total of 8 electrons, or 4 pairs. We have our central nitrogen with 4 hydrogens attached to it. We already have 4 pairs of electrons on the page, which is what we wanted. We cannot put any extra electrons around hydrogen because it's in group 1A. It can only have the 1 pair attached to it. So as soon as we put this in brackets and show that it has a charge, then it's good to go. We'll do one more here. We have CO2. Carbon has 4 valence electrons, and then oxygen has 6, but we have 2 of them there. So we're going to have a total of 14 electrons, or 8 pairs. So our carbon is the single one. It goes by itself. We'll have an oxygen and an oxygen. So we fill up the oxygens. They need a full octet because they're past groups 1, 2, and 3. And if we count how many pairs we have on the page, we've got 1, 2, 3, 4, 5, 6, 7, 8. But we're not done. We haven't checked that central atom. We haven't checked the carbon. The carbon's not full. It needs to have 8 electrons around it. Right now it only has 4. So we need to put a couple more there. But that gave us 10 pairs. Now we have too many. And that's when you know we're going to have a multiple bond. Multiple bonds can only form between certain elements, and it's on your rules on the page before, but those elements, we refer to them as CNOPs. These are the only ones that can have a double or a triple bond that can form multiple bonds. So between carbon and nitrogen, carbon and oxygen, carbon and phosphorus, sulfur and nitrogen, between any of those 5 elements that are there, we can have a multiple bond form. So since we have too many electrons, that's our hint that we need to do this, we're going to take a pair of electrons from the carbon. We're going to take a pair of electrons from this oxygen, and it doesn't matter which one you pick first here. We're going to then share them. So that's going to become a double bond in that position, and these go away. We're going to need to do the same thing again because we still have 9 pairs if we counted them up. So if this other pair is going to be shared, we're not going to share it with the same oxygen there because we want them to kind of be as spread out as they possibly can. So that means it's going to share it then with this one. If you only had one sharing, you would just pick one side. It wouldn't matter which one you shared it with. But since we do need to have 2 of them being shared, it'll form a double bond there, then we'll just take one from each. So our new structure, with these electrons being shared in the middle, will look like this. And actually these outside electrons are going to shift around a little bit. Instead of being kind of straight on those sides, it's going to be kind of diagonal like that. They're going to spread out as much as they possibly can. Okay. The next couple here, I'm just going to show you real quick. You have 1 plus 4 plus 5 for a total of 10, or 5 pairs. Since there's just one of each, you just connect them in order. If you fill up your lone pairs of electrons that you need, it would look like this. And if you counted them, you would have way too many. So we're going to take a pair from carbon and a pair from nitrogen, and we're going to share those. That still has one pair too many. So we're going to take a pair from carbon, a pair from nitrogen, and we're going to share another one. I can't take any and share with sodium, first of all, because it's not on this list, and it has no electrons to share because it's in group 1A. But now we have a triple bond between carbon and nitrogen to have our 5 pairs that we're allowed. For nitrogen here, we've got 5 plus 6 times 3 plus 1 more for that charge. So that's going to give us 24 electrons, or 12 pairs. The nitrogen's in the middle. You've got your oxygens. They get a full octet. And you can do your dots like this. They don't have to be larger dots like I was doing. Nitrogen does need to have a full octet as well. And if you counted that up, we would have 13 pairs. We would have too many. So an oxygen can't share with another oxygen because they're not bonded to one another. So this nitrogen is going to lose that one. It's going to be sharing with one of the other oxygens. It really doesn't matter which one you pick. We can pick any of these 3. And in reality, it will actually kind of switch around which one it's being shared with. And the last thing is just to show that it's an ion, and it would be in brackets like that. There are some exceptions where you can have multiple bonds, not multiple bonds, but more than 8 electrons around that central atom. We can have an expanded octet. But we're going to talk about that just a little bit later. So on your assignment that you're going to be working on, we're going to cross off some of those that would fall into that category. So we're going to cross off number 2, and we're going to cross off number 4. And you're going to have 2 of these here that are going to be extra credit. So 11 and 12 on your assignment will be worth extra points. And I kind of skipped over this, but this was kind of a summary of the different types of bonds. We don't have metallic on here, but this is kind of a good example of how covalent and ionic bonds contrast. And then to finish up the notes, we've got a chemistry cat. A covalent bond yells at an ionic bond. Didn't anybody ever teach you to share?